Hey, good morning. Okay, so what we're going to do is we're going to continue. We're going to go over an advanced example of AVL trees. And then what we're going to do is we're going to go over and review some more in-depth binary search tree questions before we go into max and min heaps for the rest of this week. Okay, so in the previous lecture, I was showing you this example where we were starting to put elements in, and every time I was putting in an element and then printing out the in order, pre-order, post-order, and level order traversals. And we can use this to see how well the AVL tree is balancing. And so here we had 15 and 10. And then what happened is we were inserting 6, and it notices that we have a lack of balance. So then we would want to perform what we're going to call single rotation right that will make 10 the root and 15 its right child. Like so. And then from there we'll put in 25. And then what we're going to do is we are going to start putting in more, we're going to put in 30, and now notice that 30, we're starting to get some bad balance over here. And where we violate our balancing rule is here at 15. So what's going to happen is 10's right child is going to become 25, 25's left child is going to become 15, and this will be the new tree that meets the balancing requirement. Now we're going to do the same thing. We're put in 12, and here, this is where things get a little interesting. We have something like this. And we're going to talk about this in more detail, a phenomenon called zigzag, where it goes in one direction and then the balance goes in, it changes at one point. And so what's going to happen is when we change everything, if we just use this normal rule, what would end up happening is we would move over, 15 over to, we would make 25 the new root, 25's right child, left child would become 10, and 10's right child would become 15. Now, where the issue is that at this specific point, it's still not balanced. So our approach didn't solve the problem. So does anybody have any ideas on what we might want to do here in order to actually solve this problem? Bear in mind, we still have 3 and 1. Any ideas? Yes. Okay, so the thing we should bear in mind, it's a good guess, and it's on the right path, and I'm going to get to your guess in a moment. The thing is that we are local in this particular node. So we need to know this particular information. So getting to the subtree is the right path. You're thinking along the right things. So I'm going to try your guess. Okay. So what we don't want to, I see what you're saying. So we don't want to end up back here, but we want to maintain balance. So what we see and what we know is that 10, 25, and 15 are kind of where we have our problem both times, right? So this is before and this is after. So what we know is that the ordering is 10 is less than 15 is less than 25. So that means one potential solution should be 15, 10, and 25. 25's right child would still be 30. And then what we need here is 10's new right child, should be the left child of 15. So if we make this 12 and 6, we are now able to make that work. So now we're kind of combining your two guesses into one here. So what we're able to do is we're now able to say, we're going to call this a double rotation. And then we can see how we would want to get the grandparent, parent, and child to perform this rotation. And so we have to consider this from two different directions. We'd have to say double rotation, this case we are going right. And then the other way, if we had this initially, going back to the previous animation, we could do the same thing where this is a double rotation left. All right, so double rotate. After the child's rotated, it will still not be balanced. So we're going to create our code here. Excuse me, let me go back. Actually, this is that just says the same thing. I just drew it up. So in this function method where I have in AVL tree, I have check rotate, and then I call for left and right. And then I have this scenario, if the left height is greater than the right height plus 1, then I want to rotate right. Otherwise, if I say the max height is still greater than, for this case, right plus 1, that means we haven't achieved the balance. And now what we're going to do is we're going to create the pointer to the grandparent, the pointer to the parent, and pointer to the child. So we have the current pointer right, and then we have current pointer right, and then I'm doing that zigzag. So now we're coming back left. Does everybody see that? All right, so let me take you back to the animation. So we have this portion of the code. And so what's going to happen is we would rotate left, and it didn't work. So now we would be checking the max height, and we still have 3 and 1. So now we violated it. So now we're going to set current pointer equal to a grandparent temp pointer. Then its parent pointer is going to be current left. So we're going to see that it's there. And then the child pointer is going to be left right. So it's going to point at 15. So the first thing we want to do is set parent's right child equal to child pointer's left. So parent is here. And so that was the situation where we're going to make 10 here. And then we know this works because 10 is less than 12, is less than 15. So that's going to be there. So we now see that the pointer has been updated in red. The next point is grandparent left is equal to child pointer right. So in this case, the child pointer is here, 15, and its right pointer is null. And that's okay, that's what we would want. And we see now that the left pointer of the grandparent is equal to that null pointer. And then we're going to say child pointer left is equal to parent. So instead of pointing to 12, we now want it to point to 10. And that's what's going to happen here. And then child pointer right is going to point to grandparent. And now we see that it's pointing to 25. And then we do cur pointer is equal to child pointer. What you're going to see is this tree again, but it's going to be cleaned up. So this was the original child, this was the original parent, and this is the original grandparent. And now the cur pointer is pointing here. And then when we got a scope of this if statement, the grandparent, child, and parent are all gone, and now we have our balancing for the tree. Does everybody see that? And now in this particular slide, it's the same thing, but in reverse. I would say if left height is greater than right height plus 1, first I would do rotate right so we can balance it out. And then we check the max height of the right is greater than the max height of the left. So if I rotated right and it didn't work, now I have the imbalance to the right. So now what I would do is I would set the grandparent equal to the current pointer, the parent equal to the right pointer. So this would be like 20 and 27. So this would be parent, and this would be grandparent, and this would be 22. Current pointer, right, left, right, left. So this becomes child. And then I do the same thing where I would eventually want it such that the current pointer is at 22. its right child is 27, and its left child is 20. So now we've performed that rotation and we've done this balance. Okay, does anybody have any questions about that? Okay, so when I run make test AVL, we will now see that I fixed the balancing issue with my, did you have a question? Correct. Okay, so the question is, do we check for null? And the answer is, first of all, in the max height method, I'm constantly checking for null. In the event that this is greater than this plus 1, if the right is guaranteed and I was able to perform a rate rotation and it's still not met, therefore I'm guaranteed, sorry about that. I am guaranteed to have a parent that looks like that. So I'm guaranteed, so there's no need for it. Those are a good question. And any follow-up questions? Let me check the chat real quick. All right, so here when I run make test AVL, we will see that I have the level order traversal of 15, 10, 25, 6, 12, and 30, and it matches out in our pre and post order traversal as well. And then when I run make test AVL, it goes all the way through. And then when I delete, what I do is I do that normal deletion and then I check the balancing again. And we'll see that I maintain this level order after deleting everything. So here I would delete, insert, insert. Then I check to see if it's with contains. I run minimum and maximum function, just like we did previously. Deleting, I would delete 25 from the tree and we maintain the level order. Delete 12, delete 15, just like I did with the previous check of the tree. All right, so what I would like to do is I'd like to walk through an advanced example, something that you might see on a homework assignment or a test, where you'll be expected to put in several elements into an AVL tree and be able to balance them. So first we have 15, so 15 becomes the root node. And then 7 becomes the left child of 15. And then initially when we put in 4, 4 becomes the left child of 7. So what should we do here? In fact, let me leave open the chat so that way those of you in the chat can participate as well. So what should we do here? What's the next course of action? All right, so we have, so Fancon says, balance the tree. How should I do so? That is correct. What's the term that I've been using? Yes, Jenny? Yeah, we're gonna do a single rotate right. So we're gonna see that that's what's gonna pop up here. I'm gonna check the balance and we're gonna see that it's violated here. So we're gonna do a single rotate right. So what that means is we are now going to make 7's right child 15 and then the current pointer there 7. Does everybody see that so far? All right, so let me check to see what's going on in the chat as well. Right rotation, very good, Jonathan. Okay, so now we're going to insert 2. And as of right now, we are perfectly fine. We have not validated our balance anywhere. So if I put in 3, what's going to happen is I'm going to move up the tree. And then we'll notice here that I have 2 and 0 at 4. And so I would want to single rotate right again. And so then I'm going to move it over. But what do you think happened? What's wrong with my animation? What went wrong here? So before it was here at single rotate right, and now it's here. So what's the issue? Yes. Very good. So what we need to do is we need to do a double rotate. So if I were to draw this out of what this is going to look like, what's going to be the left child of 7? So let me do 7 here. What will be the final left child of 7? All right, so in the chat, let me check the chat here. Chat says 3, very good, Fang Kong. So Fang Kong is correct, it should be 3. And so what's 3's right child gonna be? 4, very good. And what's 3's left child gonna be? 2, there you go, good job. All right, so then it's 15. So now we have a balanced tree. So if you see on an exam, you get in a situation where you have this zigzag, it's going to be a double rotation. And so double rotate left, and now we have the exact tree that you all derived. And so on the exam, and I'm going to reemphasize this in a little later slide, but on the exam, when you have an AVL tree question, you can be assured there will be at least one double rotation in the balancing. And so now when we do 1, we're over here. And so when we check the update the balance, what's going to happen here is we're going to now see that here on the right we have 3, and here on the left we have 1. So we're going to do a single rotate right. And what should our final tree look like? Let me bring up the chat here again. So what is going to be the new, so here we are rotating about 7. If we're doing a single rotate right, what's going to be the new root of the tree? Any ideas? If I'm rotating right, what should be the new root of the tree? 3, very good. So what is 3's right child going to be? So Luke said the right answer is 3. So what's 7? Very good. And so what are the children of 7 going to be? 4 and, that's what you're going to say in the back, 4 and 15. Very good. And then what's 3's left child going to be? 2, very good. And it's just going to be the normal tree here. So that'll be 1. So now we have that balance. So that's exactly what happened. Very good. Okay, so now we've inserted 1. And so now we're going to insert 18. And now what's going to happen is we're going to bring everything up here. And we have 3 and 2. And so at this point, we're not doing any rebalancing, excuse me. So now if I put in 19, what do you think is going to happen? Let's go through it step by step. What do you think, where is the imbalance going to occur? Which node? Yes. Okay, so node 18, if we go here, let's go up 1. You're thinking along the right path. So here we have 1 and 0, which means that node 18, this subtree is balanced. So let's go up 1 more. So at 15, what's going to happen? It's going to be unbalanced. And so we're now going to have 2, and now we're going to do a single rotate left there. So we are going to rotate this way. 7's new right child is going to become 18. And then 15 is going to be the left child of 18. And then 19 is going to be the right child of 18. Just like so. All right, and if I put in 20, now let's see what happens. So 20, we're going to move up. We're going to have a balance there of 1 and 0. It's going to be 2 and 1. And now it's going to be 3 and 1. So the imbalance is going to be here. And then what's going to happen is I'm going to single rotate left. So 18 is going to be the new root. And then what's going to happen here is we're going to see that 18's new left child is going to become 7. It's going to be here. 3's new right child will be 18, and 7's new right child will be 15. And so that's how we end up with that tree. And then if we moved up, we would see that it works fine. All right, so does anybody have any questions before I move on? Okay, so a couple quick comments about AVL trees. So these are what are known as perfectly balanced trees. They are going to have the best possible balance at the end of any given operation. So no subtree is going to have a max height of a difference of greater than 1. However, we have to call this max height method several times. So that's recursive. So it takes a lot of time. And especially if we have to do a double rotation. And so as a result, AVL trees are not very dominant in industry. They're used in scenarios when you want to have a perfect balance, when you want to have a guaranteed worst case lookup time, and you're not doing that many reads and writes. So you're going to do a lot of initial reads, sorry, a lot of initial writes, excuse me, and then you just do a lot of reads later. So things like databases. So databases are good for this. Although we're going to be learning about B trees next week, which are also prominently used in databases. And as I mentioned a little earlier, there'll be an AVL tree exam problem, in which there'll be at least one double rotation. Okay, so does anybody have any questions before I continue? All right, so what I want to do for the remainder of lecture is I'm going to be going over some common interview questions about binary search trees or binary trees to reinforce some of these notions that we've been discussing over the last 2.5 lectures. The first one, invert a binary tree. So what we have here is we have an in-order traversal of 1, 2, 3, 4, 6, 7, and 9 on this tree on the left. On this tree on the right, the order is now 9, 7, 6, 4, 3, 2, and 1. So this tree is inverted. It's in the exact opposite order. So there is a simple way to do this. So the first question I'd like to ask you is, what are some of your guesses? How do you think you might want to approach this problem? Yeah, 1 and then 2, yes. Okay, so we have a recursive solution, very good. So that's one aspect of what we want to do. We want to be recursive in our approach. So what specifically do we want to do in our recursive? Oh, so there's typically a general rule. We have to keep the nodes in place. So we can't do something like a post-order traversal where we then put everything in the opposite order. These nodes, like this node 9 here, is in the same location in the data heap that this one is. But the idea of a recursive solution is the correct approach. So does anybody have any ideas on what we might want to do when we do our recursive solution? Yes. Absolutely right. So here, what we can do is we can do a swap where we would have 4, 7, and 2, and then initially we'd have 6 and 9 here, and then 2 would initially have 1 and 3. And then we would go this way and then swap the children, and this would become 9 and 6. And then when we go this way, we swap them, and this becomes 3 and 1. So what is the ordering in which we do the operation first, and then go to the left, and then go to the right? We have 4 of them. We have in order, post order, pre-order, and level order. Yes. This is a pre-order traversal. So we're going to do a pre-order traversal of the tree, and then we are going to swap the pointers. Okay, so the reason why it's interesting is now you've demonstrated several concepts and understanding of pointers. Yes. Okay, so you could do post order, but it's going to be right, and so you're basically building it up. But what ends up happening with doing the pre-order first is if you're doing post order, you're doing right, middle, and then left. Oh, sorry, you're doing right, left, and then middle. You will get the correct solution, but what's happening is you're maintaining all the orders and kind of working them. Whereas with a post order traversal, you'd be going down, doing the right one, then you would be going back down the tree. So you could do it both different ways, but I'm going to elect to do the in-order traversal, pre-order traversal. Excuse me. So here, what I'm doing is I'm swapping the child pointers and then recursing. So the first thing I do is I create a temporary node pointer, and that points to left. And then cur left is going to point to cur right. And then cur right is going to point to cur temp, which is now pointing at 1. So now we have 4, 5, and then 1. So we've reversed that tree. So now it looks like this. So now if we swap the initial nodes, we've inverted the tree halves, just like I drew up before. So we can see here that I had 4 and 8, and now I've swapped these. But we see here that 4, 1, and 5 is the same as before. So then we can do a pre-order traversal. In this case, 8 doesn't swap, but now we can say that 4, 5, and 1 are now swapped because we've swapped these nodes. So in the private method, what I've done is I have a public method where I just call invert tree and I pass it to root. And then I call this cur pointer. And now let me go back to BST because I want to see if you all remember why I'm doing a very specific thing. Oh, that's AVL tree, my apologies. E tree. Does anybody remember for this BST node, you see how I have the pointer, but then I have an ampersand after that? Does anybody remember why I call a BST node pointer by reference? Yes. So you can directly change the pointer. Okay, so you can directly change it, and then there's a second half that I want to put together with that one. So you can directly change the pointer and what? Not move any of the nodes, but what's going to happen, like if I took this out, what would happen? Does anybody remember from when we were going over binary search trees last week? Yes. Okay, so we're building a new tree, but what specifically, you all are you're all in the ballpark. What specifically will happen if I were to run this code and I were to take that ampersand out? What would my final printout be if I printed out the in-order traversal? So I had this tree, if I said 4, 3, 2, 3, 1, 6, 5, and 7, right? If I were to take that ampersand out, before it would print 1, 2, 3, 4, 5, 6, and 7. What would it print out if I took that ampersand out? What would be the final printout of the tree? Yes. Not quite. Anybody else? Yes. It would stay the same. And why would it stay the same? Yes, we are. That's what that was the and part that I was looking for. So this is a copy. And what I'm going to do here is I'm now going to say, all right, I don't want to pass a copy. I want any change I have to this pointer to be returned when we go out of that method's scope. So now what's going to happen is when it changes, we will now have the reverse ordering. Does that make sense? And so here's the code that I was showing you. And then I recursively call left and right because I'm doing this in a pre-order. However, if you do an in order or a post order, they would both work as well. And so what I'm going to do is I'm going to run make invert tree. And we're going to see that I have a pretty large tree here. And if you run in order traversal, what you're going to see is that it should be in the exact opposite order after the inversion. Okay, so does anybody have any questions about that? And let me check. Oh, we have a comment in the chat. So Brandon says nothing. So Brandon, I take it you were responding to the ampersand, and that's absolutely right. Okay, so next problem is kth smallest element in a binary search tree. The problem states, given a binary search tree, write a function kth smallest to find the kth smallest in it. So if we say the first smallest is we're going to pretend I properly deleted that one. All right, so the kth smallest in that case is going to be 5. I'm sorry. Wow, hold on. That's just blatantly wrong. Can't tolerate that. That's got to be fixed. Okay, so here is if I were to do the kth smallest, the first smallest would be 1. The second smallest would be 4. The third smallest would be 5. The fourth smallest would be 6. And the fifth smallest would be 8. So how do you think we might go about trying to solve this problem? Yes. Very good. So if we did an in order, then what we would want to do is we would say, all right, this one's the smallest, second, third, fourth, fifth. So we see the in order traversal pattern, which we could use to actually get the order. So what will happen is we should keep track of, as we're finding the fifth, we need to go through the whole thing. And so we need to modify our in order traversal, keep track, and then we want to terminate. Let's say I want to find the fourth largest, right? And so I'm terminating, I go 1, 2, 3, and then I hit 4. There's no reason why I should continue to traverse the tree. I should only traverse the tree if we haven't reached the kth element. So in this case, and is often the case in interview questions, we will assume that there are at least k elements in the binary search tree. Although there's a pretty easy modification if we wanted to do this. So let me show you kth smallest. And first, let me show you the public method here. So this is the public method, and the user is passing unsigned int kth. So what I'm going to do is first I say if roots equal null, it's going to be an empty tree. We exit the program. Then what I say is the unsigned current val is equal to 0. I have not encountered any nodes that I'm actually evaluating. And I'm also creating t kth value. So if I create t kth value, what I'm going to do is I'm going to recursively call a private kth smallest method, where I'm going to pass the current pointer, which is the root. I'm going to call kth value by reference, and I'm also going to call cur value by reference. And the reason why is because every single time I want to change cur value when I encounter a new node that I'm evaluating, and I want to be able to change kth value when I'm done. Now, kth, it's an unsigned integer, and so we're just going to pass by value because we don't want it to change. All right, does everyone understand that so far? All right, so now I'm going to go find the private method. So here's the private one. And in the private method, I have the BST current node. And here I'm just passing a copy of that pointer because I have no intention of making any changes. I have no need to call by reference. But what I have called by reference are kth value and unsigned current value. The first thing I do is I have my check to ensure that I have the current node. If it's null, I just return, because if I'm doing an inward traversal, there's several times in which I will encounter a null pointer. At that point, we just want it to return. We don't want to mess with anything else. Next, I want to recurse left. So to do an inward traversal, I want to go left first. So what I have in this if statement is first I check to make sure that the left pointer is not null and that cur value is less than kth. And so what will happen is if I have 10, 7, 3, and 8, then what's going to happen is I'm just going to traverse. Cur node is still going to be 0. And then when I hit cur node is equal to null, I hit this and go back up. So once I go here, then I'm in the middle. At this point, then I want to increment cur value. So now I've finally encountered a node that I'm going to evaluate. Does everybody see that? So here I have 3, and that's going to be my first one. And now I have, if cur value is equal to kth, I'm going to say kth is equal to cur node data. Now notice that if cur value is less than kth is in both of these if statements. So let me scroll down just a little bit so we see the right. And now what's going to happen is when I do cur value is less than kth, that means if I've incremented it and I've found the value, there's no reason for me to recurse right. So that means I should only recurse up. So no matter where I go, as I go up the tree, since we have unsigned cur value with a call by reference, this means that we will ensure that, let's say I'm deep in a tree and I have several recursive calls to go back up. So I've gone left, left, right, left, left. So then when I start going up, I wouldn't make all these other recursive calls the other way. This will ensure a faster solution. All right, let me check the chat. Okay, I don't see anything in the chat. And now in kth smallest.cpp, I've created this tree and I have 12 elements in it. And then I iterate through and I just say the second smallest value is, and it just prints out the result that I returned from the public version. And so I put these in out of order, and you're going to see that I'm going to print them out. And you'll see that the in-order traversal will actually give us the solutions, and it should match what we print out as well. So I'm going to run make kth smallest. And we see here that our in-order traversal prints these values out. And then 1, 3, 7, 8, 10, 12, 15, 20, 22, 30, 31, 35. Okay. Does anybody have any questions on that? And so here's all the code I just showed you. And if I'm trying to, okay, so here's an animation just to make sure that it's clear. So I have cur value, and I would keep going. I hit the null pointer, I increment 1. So now we're at 2, now we're at 3. Now we're at 5. Now we want to recurse right, so 12 doesn't have a left pointer. We increment and evaluate the sixth one. 6 does not equal 8. Now we want to go right. So now we're at 7. Well, actually, we're not at 7 yet. So now we want to go left. 20 does not have a left pointer. So now we can increment. So now we're at 7. We have not found the kth value. Now we want to go right. 22 does not have a left pointer. We increment. We're now at 8. And we see that we are now going to set kth value equal to 22. And then when we go up, we're going to see here that because 8 kth is equal to curve value, we are not going to do those recursions for the last 3 elements. So that's going to save some efficiency on our solution. So here's the kth smallest solution that I just showed you, and there's the printout of our code. Okay, so the last one I want to go over for the last little bit of lecture is a third problem called valid binary search tree. And in this problem, what's stated is, given a binary tree, determine if it's a valid binary search tree. And the problem states the following assumptions. The left subtree of a node contains only nodes with keys less than the node's key. So what we are saying here is, since it has to be less than, we can't have an invalid tree that's like this. We can say 10, 6, 4, and 1. So it's less than. This means also that I can't do something like this. I can't say, well, 10 is greater than 6, so I can have a loop. So what they're saying in that first assumption is that we don't have loops. The second assumption is saying the right subtree of a node contains only nodes with keys greater than the node's key. And then the third one says both the left and right subtrees must also be binary search trees. And so here we have 2 examples, the 2 examples stated from the website. So on the left, it's a valid tree because 1 is less than 2 and 3 is greater than 2. Here, this is an important distinction. 4, 3, and 6, which is the subtree, that's a valid binary search tree. However, this part is not, because 4 is in a place that's reserved for values greater than 5. So our algorithm should be able to detect this. So what do you think we should do? Well, I would say the very first thing, first we're going to check the null pointer. And the important point is that a null pointer is a valid binary search tree. It's an empty tree and it's valid. Does everybody understand that? So I'm going to give everybody the opportunity. What do you think we should do here? What's our test? So I'll give you a hint. If we get past this current node, then that means that, and the current node is null, that means I have a node that contains a piece of data, right? So what are all the scenarios? Let's say I have 10 and I have our root. What are the scenarios I would need to think of that are a valid subtree with just the root, with just the child pointers of 10? What's one possible scenario here? Yes. Okay, so here we have 6 and 8. So let's even disassociate this from data even further, okay? So first of all, what you said is absolutely 100% right, but now I have nodes. So one possible approach is that I have 2 valid nodes as children that are not null and contain data. So what's another scenario? So I have 3 potential scenarios here, of which you've identified the first one. What's another one? Yes. One child that's null and one child that's not null. Very good. And so what does that make my third option that I need to consider? If both are valid children, or if one is a valid child and one of them's null, then what's my third choice? Both of them are null. Very good, right? So those we have to consider that at every level of the tree. So here's what we're going to do. I am going to create two variables, left check and right check. So what I'm going to use these to do is to check if I have a valid left subtree and a valid right subtree. The first thing I do is I say, well, if core node is equal to left, I'm going to set left check equal to true, because a null pointer is a valid binary search tree. Next, I say, well, if core node left is not equal to null, and then left data, so now I'm looking at the left's data. So in this scenario, I would say 10, and this would be valid, but it's like 12. So the left's data is greater than the current node's data. Does everybody see that? In this case, there's no reason for me to traverse any further. The moment I know that this case is violated, I don't need to check down here at all. No reason. And I'm going to do the same thing. Else if core node left does not equal null and core node left is less than or equal to core node data, so in this case, this would be 6. Then I would set left check equal to valid BST, and I'm going to check the left subtree. So at one point, I could have 1 and 7, and then I have a valid subtree null, 4 of those here, valid subtree, valid subtree, valid left subtree. Does everybody see that? And then I would just do the same thing on the right. I'd say if the right is null, that's a valid subtree. Otherwise, if the right is null and the right's data is less than the current data, then it's invalid. Then, otherwise, if it's not null and the right's data is greater than or equal to, then I would check with a recursive call to valid binary search tree. And then the very last thing that I do is I return left check and right check. One node by itself is a valid tree, which will pass this. Let's say I have 10, because the null will return true for both left and right. Otherwise, if there are valid, I just continue to check. And we use dynamic programming to build a set of sub-solutions to ultimately determine if this is a valid tree. So I have several tests. In my first tree, this one should fail. The second tree should pass. The third tree is empty, so it should pass as well. And if I remember correctly, test 4 is not a valid tree. So let me quickly, since we still have 2 minutes, I can quickly draw these out. So this is -10. Here I make left and right is node 1 and 2, so this is 9 and 20, and we see that it already fails here. Yes.
So you have like 10 going on to the left is 7, and to the right of that is 11. But you have to check the 11 because it's greater than 7. You have to check all of the.
Are you talking about this scenario right here that I've just drawn up?
Oh, yeah.
Yes, okay. So in this case, here's what would happen. I would say, well, 7 is less than 10, so then I'm going to recursively check here, right? So now what's going to happen is 7 is going to have 11 here and 10 there, right? Or something like this. So what's going to happen is at some point I have to check to make sure that all of these cases work. And at some point, if you have this scenario, it will return false. So, and forgive me for going fast since we're at 1 minute left. Let me show the final run. Make valid BST. And it will print out all of our solutions. All right, so today in lab, we are going to discuss the beginning of the final pre-internship project. I will just, I strongly recommend that, I know that people are trying to attend at different times based on convenience. I want to go in a lot of detail about what's expected. in the final project in terms of what you're going to work with, the amount of coding I expect, and how you're going to be working through everything. So please make sure that you're in attendance in lab today. All right, so it is 11:15. On that note, you're all dismissed.